Query optimization in a database system tries to find a cheap plan, or the cheapest plan for a given query. This is based on cost estimation. That means we want to see or estimate before we execute the query how long a certain plan will run, or what is the cost associated with a certain plan. This cost-based query optimization is based on selectivity estimation as a main ingredient. The idea behind selectivity estimation is that if you have a query and a relation or multiple relations, you want to estimate how many tuples are expected as the query result. And if you have a query, usually looks like this. So you have a join and maybe a projection, and here we have a selection and some relation and another relation. We not only want to know how many tuples come out here on top, so define results, but we also want to know for the individual subtrees how many tuples will be produced, because we need to know how many tuples are produced here, because otherwise we do not know how many tuples will be fed into the join computation, and then we cannot estimate how long the join will take if you don't know how big the inputs are. Selectivity estimation is based on learned statistics, so pre-computed statistics of the underlying data, and general assumptions about selectivities of certain predicates, and also how joins are executed, selectivity of certain joins. Then cost-based optimization is doing the following. In one way or the other, you can think of this. We have a brute force enumeration of all possible plans. So you have a query coming in, and then we can have from SQL into the relational algebra representation, and then we can apply rule-based query optimization, and then we can look at all possible plans we can think of. We can say, let's use nested loop join, we can say, let's use sort merge join, and so on. And each of these each of these possibilities will be one specific plan, execution plan, or evaluation plan. And then when we look at all of these plans, for each plan we compute the cost depending on different ingredients, and then we keep the plan with the lowest cost. That means we decide to evaluate the plan with the lowest cost. And hopefully this is also the plan that will be cheapest in practice. So in reality, when we really execute it, unfortunately, this cost-based optimization can also make mistakes. And if you're doing a mistake in the selectivity estimation or the cost estimation, it can lead to wrong decisions. For instance, you can decide that maybe it would be a good idea to use the nested loop join, but then it turns out that the input was larger than you expected, and then this can be very, very costly, but then it's too late, and the user has to wait until the query is processed. You can also depict it like this, like the different cost model ingredients. So we have for the decision making, there's like a query expression coming in. In the end, we want to know the execution cost. Many things matter. Certainly the attribute distribution. So how are the attributes distributed inside the attribute values distributed inside a certain column. Then we have some query like this. We want to know A is 42 of R, and we have to somehow make assumptions to estimate how many of these tuples qualify, right? We also have to know how big the specific relations are. We need to know if there is an index or not, and if we can use the index or not, because if we have an index and such a query here, we can say, well, we have an index on A, that's good, because then we can evaluate this very efficiently, this one query. We also discussed already quite in detail the difference between clustered indices and non-clustered indices, and clustering information describes exactly this, how the data is organized on disk. And all together gives you in the end an estimate of the execution cost, and then you can, based on this cost, pick the cheapest plan. So when we talk about selectivity estimation, we should first recap what selectivity means. So if you have a selection with a certain predicate, then the selectivity is defined as the number of tuples that come out of this query So the selectivity applied on the relation R divided by the cardinality of the relation R itself. So it's a fraction of qualifying tuples. For the join, the equation looks of course a little bit different, but essentially it's the same thing. What can come out of a join in the maximal way is all combinations of the tuples from the left side and the right side, which is simply the cross product or the Cartesian product. So the ratio that is here, the selectivity, is defined like the true result of the join divided by the maximum size of the join results. That means the join size divided by the size of the Cartesian product. And the size of the Cartesian product or cross product is nothing else than the product of the two cardinalities from R and S. Yeah, so this is very important, how this definition looks like and what does it mean. Some more fundamentals about cost estimation. Now we have a relation R and we make certain assumptions about it in terms of what we know about the information or the data stored into R. First of all, we assume that we know how many tuples are contained in R, and we denote this by T of R, tuples in R. We also assume that we know how many distinct values we have for a certain attribute A. And we can extend this to also considering multiple attributes at once. And with these assumptions, we can already come up with some simple cost estimate. Let's say we have a query of the form, like before, a selection that checks if a certain attribute has a specific value. Here we check if A is 13,434 inside relation R. Now how can we use this information above, if you assume that we have it, to estimate how many tuples come out of this query? Well, it's a simple estimator, but what we can say here is that we know that there will be, or that there are, V of RA many distinct values for attribute A, and we want to query specifically for 1. That means we have a fraction of 1 divided by VRA of the tuples in R. How many tuples do we have in R? Well, T of R. So we multiply this fraction by T of R, and this is our estimate of the number of result tuples that come out of this query. In the undergraduate course, we have seen more of these equations or more of these formulas for different operators and for different predicates. So how can we derive statistics based on the data in a database and store it, and then in the end we can use it for query optimization? So how can we estimate this? Well, the answer is we run through entire relations or tables in our database, and then we compute everything necessary that we need to do a proper cost estimation. Modern database systems, they have special commands for triggering this. In Postgres it's called analyze, and every now and then you can trigger this, or it can be triggered automatically, and then these statistics that you gather are up to date and allows the query optimizer to make proper cost estimates. So what about these values for attribute A? So if you have very few distinct values in A for a certain attribute A and in a certain relation R, that means if VRA is very short or not too big, let's say, then it's feasible to store one counter for each value of A. So if you have, let's say, in toy example, you have 5 values of A, 1, 2, 3, 4, 5, then you can say, well, 1 appears let's say 17 times, 2 appears 5 times, 3 appears, and so on, right? And then the query comes in and says, okay, we have R, how many for A is 1, and then you look up saying, 17. Yeah? And this will be, of course, no estimate, it will be an exact value for the number of qualifying tuples, because there are 17 that have A as 1. But sometimes or often there are too many distinct values of attribute A, so you cannot have this counter for each value of A separately. What you do then is to group different values together and have a counter for groups of these items. Yeah. What you can have in addition to these coarse overview of occurrences is to have counters for special values. For instance, you have the most frequent ones. For these you can keep these exact information, and for others you keep only these groups information. Computing for groups of items these frequencies of occurrence, this is exactly what is done in histograms. In addition, you can have also parameterized distributions of the values in A. And we will talk mainly in the next slides about histograms. So here are some data. Let's assume these are the real values of a column A in a database table R. So we have R, right? And there are multiple columns, and there's one column A. And let's say these here are, all of these are here just the values of this column. So if you're looking closer, you see it looks like these are the numbers between 1 and 20, right? If you're looking even careful, then you see that 1 is missing here. But anyway, here you see, let's say, values between 1 and 20. And then 1 will be just a frequency of 0, right? So now the query comes and asks for A is 3. How many do you see? Now you have a 3 here, and so on, right? And now if you have already information about these distributions, or the frequency distribution of the individual values, and then you can say, okay, 3 appears whatever times, right? And then this can be either exact or it can be an estimate. If you're displaying this information in an exact way, like we do here, in a histogram style fashion, where you have these histogram bars, you see for every value from 1 to 20 how many times it appears. This is not a histogram in the sense of having histograms approximating frequencies. Here we have one histogram bar for one value. So this is not an approximation. That's important to understand. So in the example I had earlier on the previous slide, I was asking for A is 3 of R, and now we see if we had this information like this in an uncompressed, so in an exact fashion, we just see here 3 appears 19 times. So that means the output here is 19 tuples. Yeah. In addition, or an alternate way to represent it is not storing the absolute numbers here, but to normalize these frequencies to 0 and 1. Yeah? This is like an alternate representation, doesn't matter. You just have to know what you did, how you stored it, in order to make the correct calculations. So now this is like a histogram style, I said, and later on we will talk about histograms in more detail. So what is a histogram? What we will see later on. A histogram, and I guess you have seen this, everyone has seen this in undergraduate courses already. A histogram is basically something like this, what you see here, but it has like multiple values put together in groups, because then the representation is cheaper. Here you have one value on the x-axis and one frequency value for it. Now let's say you want to save a bit space, and you put all of these into one group and all of these into one group. Now you're summing up all the frequencies, 6 plus 19 plus 2 and so on. Not sure what that is, but you're writing now the frequency for the entire first group and then also for the second group, whatever, f prime. And this is of course now a very crude approximation, because you forget how many, what is the frequency of the individual numbers here, but you remember what is the overall frequency for all numbers in this group 1 or in the group 2. Yeah, we also call this bucket 1 and bucket 2. And now if a query comes and says, okay, how many times does 3 appear? In this kind of style histogram, which is an equi-width histogram, you would take then the sum of the frequencies for the first group, where 3 falls into, and divide it by the width of this cell, which is 10 in this case. And this is, of course, not anymore exact representation like the original diagram was, but here we have only an approximation of the number of times a tuple with value 3 appears, right? But this maybe was too crude, the approximation. We can have a bit more storage, right? So we can also put the first 5 into one bucket and the next 5 and so on. So now we have a histogram, equi-width histogram with exactly 4 buckets, right? And now the approximation is already getting better, because now there are only 5 values put together. But the same situation happens. You want to know how many times A is 3 in the database. And then you have to see what is the overall frequency of this bucket. And then you're dividing this by 5. And this means, it's clear already, that you're treating all of these 5 values the same way. Even so, you see that 1 does not appear at all, but 3 appears 19 times. And if you're treating all the same way, you see that you're making, of course, a big mistake when you want to have the estimate for A equals 3. But that's not avoidable, because you wanted to have an approximation by grouping values together. You can also describe distributions of data using distribution functions. For instance, a normal distribution with mean and variance. So you're fitting a normal distribution to your data, and then you're storing, in this case, only 2 parameters, the mean and the variance. And now you can use this to make an estimation how many times like A falls into a specific region, or like a range, or like exactly is equal to 3. And what we have seen earlier was exactly the summarization based on these buckets or cells, and this is what we call histogram representation. Here's an illustration taken from Wikipedia showing the density function and the distribution function of normal distributions for different parameters of the variance and the mean. So if you're saying now, okay, now we have 2 options, we can use histograms or we can have distributions fitted to the data, what is better? Difficult to say. The problem with fitting distribution functions, as you have seen for the normal distribution case earlier, there are 2 parameters, right? And somehow this suggests already that this is not as powerful as if you have histograms and you're giving yourself, like, let's say 100 of the cells, so 100 groups, and that you use to model the data distribution, because these distributions are also limited in the way they can express weird shapes of distributions, right? If you have an arbitrary distribution like this one here in the background, it looks a bit normal, yeah, but it's of course not really normal. And you have now different ways to approximate this. There's one illustrated normal distribution here that you might think is a good fit, or this one here, but you're doing still many mistakes, and it's difficult to represent all of the data with one single normal distribution that has only 2 parameters, right? In histograms, you're much more flexible. You can have, in this case, histogram cells looking like this, right? And you see perhaps that this might be already quite a good fit of the underlying data. And if you're not happy with it and you can tolerate spending 2 more times the number of information stored, then you can have even a better fit by having more histogram cells, right? So you have maybe something like this, right? And you have like something like here and so on. So the more histogram cells you give yourself, you have to pay, of course, for the storage, but then the approximation is also better. That means histograms are usually more flexible, or they are more flexible than distribution functions. Here you see not a normal distribution, but some polynomial fit of degree 6. There's some tools that you can use to make that fit. Don't have to do it by hand, and of course in a database system anyway you would write a program doing this. So here you see in this green line, hopefully now it's purple line, now it's green again, you see this polynomial fit, and you see that it's working quite well for some values, but for others it's also making quite large mistakes. Well, but you have only limited number here of parameters, and if you have a histogram which has very few cells, you will also do mistakes, right? So there's no silver bullet that gives you for like a few parameters only a perfect fit for arbitrarily looking distributions, right? And this distribution is also like the underlying frequencies here are also very harsh, right? So you have like a small value and then a huge value together. This is difficult to fit for such distribution functions. The easiest way, or let's say the cheapest way to store information about a distribution is to assume uniform distribution. And if you recall from the previous plot how spiky this distribution was, of course you're doing a huge mistake if you're assuming uniformity. But still, you can do that, and then our approximation of the spiky histogram from before, or the spiky distribution, the red ones here, would be just like this flat plot under uniform distribution assumption, and you can already see that you're doing many mistakes, right? For some values it works quite well, for others it's a disaster, but however, it's a very compact representation because you only need to know the average value, right? So you're assuming a uniformity, that means every value appears 6 times, so you're just remembering 6. And someone asking, hey, how many times does A is 4 appear? You say 6 times. And how is A equals 7? How often? 6 times, right? And A is 14, 6 times. So it's easy to evaluate, easy to store, but of course it's not a good fit usually, right? If the data is not uniform. And real data is usually not uniform.